Hello everybody. Welcome back to our videos. We're continuing on with section 4.1, some more fun with this related rate stuff. I know you guys had a great time with this during the first video. So we're going to keep the fun rolling here and do a couple of more examples in this video. All right, before we jump into this though, I want to remind you again of our problem solving strategy. Now, as I mentioned in the first video, these problems are not like teaching you the power rule or the product rule or something like that, where I can say this is how you do it every single time. Okay, I'm showing you some examples that might be helpful for some of the problems you work on, but know that each problem kind of requires its own approach, especially depending on the type of formula you need to use. But this problem solving strategy here can kind of give you a framework to work with. And big part of this, remember at the beginning, drawing a picture. If there would be a related picture, that can be a very powerful thing to do and helpful thing to do. Identifying variables, also an important step. And then after that, finding an equation, taking the derivative, and substituting in values. And I highly suggest you do this stuff because often I'll see students will just jump in trying to solve a problem without taking time to organize themselves. And taking that extra time to organize, figure out the information you don't have, assign variables, that can actually save you time in the long run and help you find a shorter path to the answer. Okay, so let's look at this problem. So we're told that a water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters or 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, a lot of stuff going on in this problem. So first of all, notice that we're told that the water tank has the shape of an inverted circular cone. So circular cone, I know, is something that kind of looks like this. It's my best drawing edit. That's kind of terrible though. Hold on, let me try that again. So cone kind of looks like this. That's a little better. But they tell us that it's inverted. So what does that mean? Inverted, if you invert something. Oh, right. It means it's been flipped over, right? So it's not sitting as I've drawn it here. It's actually the other way around. So the cone is going to look something like this. Okay, so that's the tank. And the tank is being filled with water, so I'll use this to show the water kind of going in. All right, and we're told that the radius of the cone, so from here out to one of the sides of the circle, that length is 2 meters. And then the height of the cone is 4 meters. And then we're also told that the rate at which it is filling is 2 cubic meters per minute. And let me try to write that better. 2 cubic meters per minute. Okay? And they want to know the rate at which the water level is rising when the water is 3 meters deep. And so we're looking at when the water level is up here. So that's a distance of 3 meters. How fast is the water level increasing? Now, a couple of things about this. You may be thinking, well, if the tank is being filled at a constant rate, then the water should be rising at a constant rate, right? But is that true? Because think about if the water level is where it is in this picture that I drew, which is when it's at 3 meters, versus, let's say, when there's not very much water in it, so let's say it's down here, maybe like a meter or less than a meter. Is the water level going to rise faster here or here while it's being filled? Well, hopefully you're saying that it would be this one over here, right? Because you imagine if there's less water in the tank, and if you're filling down at the bottom there, at the bottom of that cone, then the water level is going to rise faster down there because it has more room to expand quicker. Whereas over here, once you get to the top, the kind of area or the amount of space you're filling is larger. So even though you're filling water at the same rate, the water level is going to rise at a lower rate. Okay? So it does make sense to look for the rate at which the water level is rising. Okay. Now let's do some label some stuff with some variables. So we're told again that the radius of the cone is 2 meters. Down here, the height of the water is 3 meters. And we're trying to figure out the rate at which the height of the water is changing. So that means we're looking for dH dt, so the rate of change of the height of the water with respect to time. And then we also know the rate at which the volume of water is changing, right? Because we're told that it's being filled at 2 cubic meters per minute. So we also know this value that I'm going to call dV for volume, dt, and that's the 2 cubic meters per minute. Okay, so when I look at this now, I see that I have an R, an H, and a V as the different variables, and T, of course, but T is just our time variable. And do we know something in relation to a cone that has to do with R, H's, and V's? Well, this problem's about water filling up a tank. And there's also this thing about volume here. So what sort of equation do you suppose we probably want to use here? Yeah, a volume equation of some sort, right? So we want to use the volume equation for a we want to find the volume equation for the volume of a cone, and you can look that up if you want to double check me, but the formula is V equals 1/3 pi r squared h. And as a side note here, you'll see that there's that pi r squared in here, which is the area of a circle, which hopefully makes sense because the base of this cone is a circle. And before we plug values in, we of course want to take the derivative. And we could do that here with respect to t. And so we could take the derivative of the v here, the r, and the h. But notice there's a problem with that, right? And the problem is that when we take the derivative of r, we're going to have a dr dt. But do we have a dr dt in this problem? Do we have a rate of change of the radius of the cone? No, right? And in fact, I should point out, right, that this r that I've just pointed out here, that's not the same as this r here, right? Because we're looking at the moment, we're trying to figure out the rate of change of the height when we're at 3 meters of water, which means we're looking at this cone form down here where the water's at, which is going to have a different radius, right? We don't actually know that value. So, crap. That probably means this problem's impossible, right? No, it's not. Okay, so let me erase some stuff here because there's a lot of lines and it's kind of hard to see what's going on. Take that out. Okay, and then for right now, I apologize, I'm going to erase this stuff here in the middle because I need a little bit more space to work. Okay, so in our drawing here, we again know that the radius of the big cone is 2 meters, and its height is 4 meters. And then we've got this water level that's right to here. And we know for the water, the height is 3 meters. But we don't know the value of the radius at this point, right? So what I'm going to do is I'm going to cut out a 2-dimensional cross-section of this tank and water at this point. So I'm going to kind of like, if you could imagine, I took like a plane and cut off a piece, okay, in 2 dimensions here. Well, what would that look like? Well, even though the top is circular, if I'm looking at it from the side, right, hopefully you would agree with me, this is going to kind of look like a triangle. Where this length here, across the top, that's going to be the 2 meters. So that corresponds to this right here. This side here, well, that's the height of the cone. So that's the 4 meters. It's already right there. There's also going to be a piece right here that comes from the water level. And I know that that is at 3 meters. And then there's still the R value here at that 3 meter height we're looking for. And you may be thinking, cool, Cody, you just drew a sweet triangle with a bunch of stuff on it. How is that helpful for us? Well, for those of you who have taken geometry recently, what we actually have in this picture are 2 triangles. And you'll note that they are similar triangles. So if we look at this one on the outside that I just outlined in yellow, and this one on the inside that I'm outlining in blue, those are what we call similar triangles. And that just means that their angle measures are all the same, even though their side lengths are different. And when you have similar triangles, it means that corresponding sides are in proportion to one another. So as an example of that, notice that this 2 and this R are in the same position in each triangle. And then the 4 and the 3 also represent the same sides, because the 4 is this big long side, and the 3 is this shorter side right here. Okay? So what we can do with that is actually set up a proportion, which would look like, and sorry, I just realized I made a mistake here. Oh, no, it's fine. So we'll set this up as 2 is to R as, let's see, 2 is to R as 4 is to 3. Okay. And we could solve that and find the radius in this moment, and you would solve this by cross multiplying. So I could do R times 4, 2 times 3, so I have 4R equals 6. Divide, and we get that R is 1.5 at that point. But what we actually need, and I apologize, I overlooked this when I was looking, solving the problem, or setting this up, is up here in our volume equation, we have R's and H's. And so we have too many, I want to kind of simplify the number of variables here. So I'm actually going to, instead of labeling this height here as 3, I'm going to label it as H. Okay, and look at what is this proportion regardless of what the height of the water is. And if we do that, then notice our proportion here, instead of being 2 is to R as 4 is to 3, we actually get that 2 is to R as 4 is to H. And if we solve that for R, so again, do the cross multiplying. So 4 times R, 2 times H, divide by the 4. We end up with R equals 1/2 H. Okay, that's again using the similar triangles. So what does that do for us? Well, what we can do now in our volume formula here is plug in that value. Okay, so we just saw that the value R can be replaced with 1/2 H. So this volume formula now will become V equals 1/3 times pi times, instead of R squared, we'll have 1/2 H squared times H. And then we can multiply that out. We'll have an h squared times an h at 1/2 squared, which is 1/4 times 1/3. If we do that, we end up with, this now becomes 1/12 times pi times h cubed. And what this did, okay, now I'm on track here, is that this now has eliminated the value r from the equation or the formula here, which is good because in our given information, we're not told anything about the value r except for r for the cone itself. We don't know the value of r at when the water height was 3 meters, which we could just find, but is also not super important for this problem. Okay, so we're still trying to figure out the rate at which the height is changing, this is also helpful for that because we only have h's in our problem. So we're looking at v equals 1/12 times pi times h cubed. And so to find dh dt, we can first take the derivative here using implicit differentiation. So take the derivative of the v over here, that's going to be 1 times dv dt, or just dv dt, equals over here, we'll have 1/12 times pi times the derivative of the h cubed, which is going to be 3h squared times dh dt, which we can then simplify a little bit more. So we have dv dt equals, let's see, 1/4 times pi times h squared times dh dt. And then we can go ahead and plug in the values we know. Okay, so at this point, we know that dv dt, the rate at which the volume is changing, volume inside the cube, well, that's the 2 meters cubed per minute. We also know the value h because we're looking for the dh dt when the height is 3 meters. So we can plug that information in. So we'll have 2 equals 1/4 times pi times 3 squared times dh dt. We can multiply out this stuff here and then divide on both sides to isolate the dh dt. Okay, and when we do that, what you will get, plugging all that in the calculator, is 0.283. And what will our units here be? Well, we have dh, so change in h, which is our height, which is measured in meters, per dt, change in time, and the only time they give us here is minutes, so it's meters per minute. So our answer there, 0.283 meters per minute. So when the height of the water is 3 meters, that height is changing at 0.283 meters per minute, which again is going to be different than what it would be at other times. Whew, a lot going on in this one. I might suggest that you go back in this video and rewatch this or rewatch certain parts if you're unsure of what we did. You can also reach out for questions. All right, that was just way too much fun, so let's do another one. So here we're told that a rocket is launched so that it rises vertically, and a camera is positioned at 4,000 feet from the launch pad. When the rocket is 2,000 feet above the launch pad, its velocity is 500 feet per second. We want to find the necessary rate of change of the camera's angles in radians as a function of time so that it stays focused on the rocket. So we want to figure out how does the camera have to rotate to be able to continue to follow the rocket. Now to do this, just like on the last one, let's first draw a picture. So we get a sense of what's going on. We can label the information we have, the information we don't have, and what we're looking for. So the rocket takes off from the launch pad, right? So this is going to be my rocket. Actually, I have colors so I can do this. Okay, and we're told that we're given this value about when it's 2,000 feet above the launch pad. The velocity there is 500 feet per second. I'll hold on for that for a second. And then, oh, we also have that the camera is 4,000 feet away. So this would be our camera here. Okay, so that's going to be 4,000 feet from the launch pad. And we're trying to figure out the rate of change of the angle of the camera, which notice the angle is formed by the camera looks at the rocket, and the angle, which I'm going to call theta, is formed with the ground there, right? So this would be the angle theta. Now, before we even start adding any variables in here, notice what have we formed here? Oh yeah, we have a right triangle, right? And we're trying to find out stuff about an angle, and notice we have two sides of that right triangle in relation to that angle. And what would those two sides be in relation to it? Well, this one looks like it's opposite. This one looks like it's adjacent, which tells us we're working with some sort of tangent function or formula here, right? So we have tangent of theta equals opposite over adjacent. And we're trying to find the rate of change of the camera's angle, which means we're looking for a d theta dt. And good, so let's put some other labels in here because I know that each of these sides is the side of a right triangle. I'm going to call, actually, you know what? I'm going to call this A for adjacent and this O here for opposite. And we actually know dO dt, right? The rate of change of the side O with respect to time. That's the 500 feet per second. And then this value for A here, is that changing at all? Doesn't appear to be, right? Because it's a value that stays constant, right? It's a constant value of 4,000, so that doesn't change. Okay, so a couple of things we need here. So we want to take a derivative of this function somehow. Before we do that, though, can we use that tangent equation over there to find the value for theta? All right, yes, I think we can. So first of all, I'm going to write this a little smaller. So we can plug in the values over here for O and A. So we'd have tangent of theta equals not O, but it would equal the opposite side, which is 2,000, or the length of the opposite side, which is 2,000, over the length of the adjacent side, which is 4,000. We can then find the value for theta here by doing inverse tan of the 2,000 over the 4,000. Okay, and when we find that value, notice that up here we're asked to find the change in the camera's angle in radians. So we'll want to do this in radians as well. So if I do inverse tan of 2,000 divided by 4,000, looks like I get 0.464 as our value for theta there. Okay, and that's in radians. All right, so let's go back to our tangent equation up here because that relates all of our variables. And another thing I know, as we pointed out, is that the value A here, the adjacent side, that's 4,000, and that stays constant. So that's not anything that's going to have a rate of change or change. So I'm just going to put that value in there. So tangent of theta equals O over 4,000. And then I'm also going to get that 4,000 out of the denominator by multiplying it by it on both sides. So if I do that, I end up with the opposite side, O equals 4,000 times tangent of theta. That's just going to make things easier to work out here. Okay, so I'm going to write that up here at the top. And again, I apologize, I'm squeezing this in. I just want the picture to be there as a reference as we're doing this. So we have opposite side equals 4,000 times the tangent of theta. And now we can take our derivative on all sides, or both sides. So we take the derivative of the O on the left-hand side, the opposite side, we'll get 1 times dO dt equals over here, we'll have 4,000 times the derivative of tangent, which is secant squared, right? Yep. Of theta. Then we have to multiply by the d theta dt. Okay. And then we can plug in the information we have. So we know that the rate of change of side O with respect to time, and that's 500, not 5,000, 500, equals 4,000 times secant squared of the value for theta was 0.464. And darn it, of course, again, I ran out of time. I ran out of space. That's being multiplied by the d theta dt. And for now, actually, I'm going to clear this out just so you guys can see better what's going on. So I have, at this point, plugged in my dO dt, which was 500. Right. So I have 500, 500 equals that 4,000 times secant squared of the 0.464. Times d theta dt. Okay, we can multiply all this stuff out and then divide by it on both sides. Okay, and when we do that, we'll have the d theta dt equals 500 divided by 4,000 times secant squared of 0.464. And I get 0.0, let's see, 9996. Okay, is the rate of change of the angle. And again, units on this, theta, the units on that were radians. dt, the time we have are seconds. So in order to keep focused on the rocket, the camera's angle needs to change, or at that moment when it's at that height of 2,000 feet, the rate of change of the camera's angle is 0.09996 radians per second. Again, if you're unsure of what we just did or missed something, I would suggest you go back in the video and rewatch a segment, and or please reach out with any questions. Okay, thanks for watching.